So good morning and welcome everyone. I think we are live now. Thank you for joining us today. I'm really happy to present here the first graduation lecture of 2021 of the Global Teaching Fellow Program of Delta Analytics. Just for those who don't know, Delta Analytics is a non-profit organization which is run entirely by volunteers and is focused on making machine learning more accessible at a global scale. I am Nicole and I'm a volunteer in Delta. And I'm really excited today to present here our really talented fellow Khalid, Saifullah, which is an undergraduate that studies computer science in Bangladesh at the Dhaka University with a passion for deep learning and NLP. So today Khalid is going to give us an amazing lecture speaking about one of his projects, which is this DALL Mini focused on image generation from text. So I would just like to warmly welcome Khalid here to our first live on YouTube. And Khalid, the floor is yours when you want.
Okay. Thank you very much, Nicole, for the introduction. So hello, everyone. Welcome to my graduation lecture today. So today I'll be talking about DALL Mini, which is a text-to-image generation model. It's a project that I have recently had the opportunity to work on. So at first, I would like to give a shout out to all the contributors who worked on the project. So these are all the people who worked very hard to make the project actually possible. So these are the agendas for our today's talk, and we will mostly spend time in these two sections, which is VQ-GAN understanding and the BART understanding section. Okay, so before starting, a little bit about myself, though Nicole had introduced me actually. So I'm Khalid Saifullah. I'm a CS undergrad student from Dhaka, Bangladesh. And I have great interest in fundamental research in deep learning. And I'm also a cinephile. I love to watch movies, and yep, that's me. So before starting about DALL Mini, I would like to I don't know if everyone is familiar with DALL, which is the actual project from which DALL Mini is inspired from. So DALL is the project from OpenAI. So in the earlier 2021, OpenAI has published this blog post in their website, and it kind of went viral in the social media. So they were showcasing their latest model, DALL. So the way the model works is you give the model a text prompt, and the model kind of generates an image for you. And the reason this is truly incredible is if you look at the generations that made by the model, and you'd see that the generations are truly incredible. I mean, these pictures, you cannot find them in the data distribution, right? And even you cannot find them in the internet. So the model has somehow learned a very good multimodal representation in its knowledge base, and kind of hallucinating these amazing images. So I was very fascinated with the results of the model. And a few months ago, Hugging Face, which is an open source AI community, so they have announced a community event in their forum. So they said that anyone can participate as a team, and every project will be given all kind of resource support and all kind of support so that the teams can build the project. So after a few days, Boris here, who is our team lead, so he posted this project proposal in the Hugging Face forum. And when I first saw this, I was a bit surprised. I mean, by just looking at the title, I mean, I was thinking this is a very over-ambitious project. I mean, how can someone think of doing something like that in such a limited time frame, and also with quite limited amount of resources? So I was a bit skeptical, but to say the truth, I couldn't hold myself, and I thought that I have to be a part of this amazing journey. So I also said that I want to be a part of it. So we worked very hard after a few days on the project, and finally we were able to finish the project within a very tight schedule. As you can see here, we started in June 24, and we submitted the demo in July 19th. So it was a very tight schedule, but we were able to finish it. And if you are interested, a little bit of short statistics between the OpenAI's DALL and our DALL Mini. So here W is representing parameters. So OpenAI's version had 12 billion parameters. So it's huge, and ours had only 0.4 billion. So DALL Mini is kind of 30 times smaller than the OpenAI version. And also OpenAI had 250 million data to train their model, and we only trained it on 15 million data. So yeah, we talked a lot, but I think let's just see how the model actually is, because our model is actually, you can test it out. It's hosted in the Hugging Face. So you can go into Hugging Face and test out the model. So let me try out some captions. So it takes around 19 to 20 seconds to generate images, but under high traffic, it takes a bit more time. So let me also try another caption in the meantime. So this one is Boris's favorite caption. So yeah, these are the images that are generated by the model for the caption here, sunset behind the mountain. So yep, I wouldn't say it's great, but I would say it's pretty impressive. I mean, considering all the constraints we have imposed upon the model, and also we have only trained it for 3 days. So that's also a case. And this one is still loading. So yep, I think it's not OpenAI level. So yeah, these are the generation for the Eiffel Tower in the moon. So yeah, I wouldn't say these results are OpenAI level, but I would say considering all the limitations and everything, I would say it's a pretty impressive result for this model. Okay. So we have seen that how DALL Mini is performing. So let's actually now dive in into how did we actually train the model. So this is basically our training pipeline. For our DALL Mini. So you can see here. Let me use the thing. So you can see here these rectangular boxes. So let's not get intimidated by these, and let's think of these as some black boxes. We'll get into the details later. Let's just try to understand the workflow here at first. So how the data is flowing through in this diagram. So at first we have this image and a caption. So we have in our data set, we have lots of image and text. So the text kind of describes what the image is about. So at first we take the image and pass the image through this VQ-GAN box here. And then what we get is a vector, okay? And then we take the text and pass it through this seg-to-seg box. And what we get is another vector. And when we have two vectors in our hand, then we know the drill, right? So this is just a basic deep learning recipe. So when we have two vectors, you just turn it into a distribution with basic softmax, and then you apply your good old cross entropy loss. And so we pass them through the cross entropy loss function. And when you have your loss calculated, you are pretty much good to go for back propagation, and your model will start training. So this is basically the story. But this was very high level overview. Now let's get into the details. So at first we will try to understand this portion here, what's happening here. So especially this VQ-GAN, what it is and how it works. Okay. So at first I will talk about some ideas first. So the first idea that will help us to understand some concept is theory of perception. So if I ask you, what do you see in this image? So what would you say? You can write in the chat if you want. So What are you seeing in the image? Happy puppy with a ball. Yep. Ugaso said I had happy puppy with a ball. Right. Yeah, I think all our dog fetching a ball. Yeah, right. Ramesh has said dog fetching a ball. Yeah, I think all of our description would be pretty much similar. And if you look at all our description, then you would see that we are only using few discrete symbols to kind of ascribing this complex image. So we are, if I tell you that these discrete symbols here, dog, ball, field, tree, these discrete symbols here kind of represent the whole idea of this image, what this image is about. So this is what the theory of perception is saying, that you don't actually have to kind of describe every inch and every pixels of the image, but you the way we describe image is with few discrete symbols. And I also see Ramesh has posted a question, and I will get back to it later actually. Thank you for the question. Okay, so this idea of theory of perception will actually help us with to conceptualize the idea of vector quantization later, which we will talk about later. Okay, so the next thing is, let's say we want to generate image with CNN. So what's the problem? What could be the problem? So there are many problems with generating images with CNN. People have tried. There have been quite a lot of work of generating images with CNN. There are a lot of problems, but I won't go into the details. One of the fundamental problem is the inductive bias. So we know that CNN have a great inductive bias for images, right? So CNN has the ability to learn local correlations in the image very, very well because of the kernels, right? So, and these inductive biases actually become problematic when you want to generate image, because when you want to generate image, you have to have a global understanding. So, so that the inductive bias actually makes CNN too restrictive. So CNN, we cannot do it with CNN. What else can we try? Well, when we think about generating something, one thing that comes into our mind is, I think, transformers, right? Because if you have been working in the NLP domain, transformers have kind of taken over everything. So people have been using transformers to generate stories, articles, and so many other stuff. So the basic idea in transformers is you do, so the idea of language modeling is you take a token and you kind of predict what the next token is gonna be. And then, so every time you take a token and predict what the next token is going to be. So that's how you kind of generate words, and by words, you kind of generate a whole story. Or yeah, so that's a basic idea. So this idea we can actually use in our case. So we can actually generate image. So what we have to do is every time we will generate pixel, right? So we will generate lots and lots of pixels, and at the end we will have in our hand a whole picture. So that's the basic idea. So let's say we have this image, which is pretty basic resolution, 256 by 256 by 3, an RGB image. And if you flatten this image, and what you get is this massive input sequence. So that's I think you are all seeing the problem here. So the problem is when you flatten image in the pixel space, your input sequence become massive. And if you have worked with transformers, you already know that's a problem for transformers, because transformers have this ability to learn global relationships thanks to the self-attention layer. So because the self-attention layers have these matrices, query and key matrix, so using those metrics, it can actually look in every portion of the input sequence anytime it wants. So when your input sequence becomes bigger, the QK matrices also becomes bigger, and this is what we call the quadratical computational cost. So we cannot actually afford this massive input sequence. So we have to do something about it. So what can we do? now I think the theory of perception idea. Yep, I think I will attend the question a bit later. So I hope. Yep, thank you for the question, Ramesh. I will try to attend those a bit later. Okay, so what we can do is we can apply the idea of theory of perception here. We won't actually use all these pixels to describe the image, but we can actually use few discrete tokens to describe this image. So what can we do is we can assign few discrete symbols at each portion of this image. And then we can flatten this grid, and we will get these discrete tokens. But now the question is what these discrete tokens actually mean. I mean, this 0 to 90, this doesn't mean anything. Well, to have a meaning, we can actually manage our dictionary, right? So in the dictionary, we will actually save. So in the 0th position here, we will save an embedding vector. Which will kind of save what this 0 token actually means. So in this 0 position, we are seeing it has a tree embedding vector. So this 0 token is kind of meaning a tree, and also this 2 token means a dog face. So your dictionary will kind of give you what these tokens actually mean. So this is a very high level idea, and also the things that I'm saying here, these are only useful for having an intuition. Don't take these as a ground truth. So these will only help you for building an intuition when we look into the VQ-GAN architecture. So this is a very basic idea that will help us to understand the architecture that we will now see. So now we have actually came into the details. So this is the Taming Transformers paper, where they have actually proposed the idea of VQ-GAN. So, and the thing that you are seeing here is a little portion of the whole VQ-GAN architecture. So if you look into the architecture here, what do you think it reminds you of? I mean, if you look into the data flow, you will see that we have an image here. We are passing the image through the CNN encoder, and we are getting a bottleneck. So this tensor looks like a bottleneck. And then we are performing some operations with the tensor. Right, yeah, Riddhi has said it's an encoder-decoder, right? And this bottleneck, we are passing through a decoder, and what we get is our reconstructed image. So as Riddhi have said, this is just a basic autoencoder recipe, right? So yep, this is just basically the idea of autoencoders. But if you have worked with autoencoders, you know something, that autoencoders reconstructions are not very good actually. So the reconstructions from autoencoders sometimes are a bit blurry, and even the quality is not very good. And so what can we do here? So, well, we know about another type of model, which is GAN, which have the very good reputation of producing very high quality images, right? So the authors have thought that they should actually include the GAN part in this pipeline. So then they have included this discriminator portion. So if you are familiar with the GAN literature, you probably know what's happening here. So what's going on is the generator. So this is the generator. It's generating an image, and we pass this generated image through the discriminator here. And then the discriminator kind of give us the verdict whether the generated image is real or fake. So the goal of the generator here would be to produce very, very high quality image, right? So that it looks very much like the real input, so that it can fool the discriminator. So in this process, our reconstruction would be pretty high quality. So this is is why they have actually included this here. So we have understood this portion of the architecture. Now let's try to understand what's happening in this quantization part. So what actually happening is the idea we have talked about earlier. So this z hat here, so this z hat is the downsampled image, right? So we had this image in our input, we passed it through our CNN encoder, and the CNN encoder gave us this z hat tensor, which is the downsampled image. And now we have talked about that we don't actually need to use this very high dimensional stuff. We can actually use few discrete tokens to kind of represent our whole image. So this quantization operation actually help us here. So the quantization operation takes this tensor and performs some operation which we'll look in detail a bit later. So then it transforms this tensor into this discrete tokens. And if you like notice that each of these tokens here have a meaning, and these meanings are saved in this codebook, which kind of relates to the dictionary idea that we talked about in the earlier slide. So in this codebook, if you go into the first index, so the first index, you will get this embedding vector. So this embedding vector kind of the eye of the dog, and this vector here, this vector is kind of representing the nose of the dog. So this codebook actually kind of, you can think of it as the image space, and the codebook length is discrete. So your VQGAN have to do a very good job to transform this tensor into these discrete tokens with only using the tokens from the codebook. So how this happens, how this happens in the training process, we will look into details a bit later. So this is like a very high level idea. And I think now we all know that what we will do with this token later. So later we will use a transformers which will help us to actually generate image using these tokens. So in this portion here, we are not actually generating any images. We are only reconstructing images. And in this process, we will learn very good embedding vectors in the codebook. And when we have learned this embedding, then we will use a transformers. And in the transformers, we will actually use the idea of language modeling idea to generate image token by token. But we are getting a bit ahead of ourselves. We don't have to look at the transformer portion now. So at first, let's actually try to understand how do we actually train this part. So I have gave you a very high level idea, like how each of these portion means, but we haven't gone into the details. So the stage one would be to train this part. And this equation here, which may look a bit daunting. So this equation represents the forward pass of this VQ-GAN model. So this model here. So this equation represents the whole forward pass. So if it is looking a bit messy, don't worry. We will actually, yep. Ramesh is asking if the codebook is learned. Yep, we are actually learning the codebook as well. So we will backpropagate the gradient through the codebook as well. Right. Thank you for the question. So now let's try to understand what's happening in this equation, which is looking a bit messy. So let's try to use some illustration and try to understand what's happening. Okay. So at first, we have a codebook in our hand. Then we take an image from our data set. Then we pass our image through the encoder, which is the CNN encoder. Then what the CNN encoder returns is a tensor, right? And we know something about CNNs, which is CNN encoders actually try to downsample the spatial dimension, or reduces the spatial dimension and increases the channel dimension quite a lot. So if we try to like infer what the shape of this tensor is, because it will help us to understand. So for now, let's imagine that the channel dimension here is 256. Okay, and also something to consider is your channel dimension here has to match with the vector dimension here. So whatever vector dimension you're using in the codebook, your tensor here will have the same channel dimension. And also, let's say that our image is of the h by w by 3 dimension, then our tensor here will have the dimension h by w by n. And this h is downsampled by this factor f, and this f here is a kind of a hyperparameter which we call the reduction factor. So how much downsample you want your spatial dimension to be. So this is something you can actually tune during the training, and it actually matters a lot. So in our case, we are using the value of 16. So let's say our image is 32 by 32 by 3. Then what would we get in the tensor would be 32 divided by 16 would be 2. So 2 by 2 by 10. So this is basically the shape of this tensor. Sorry, 2 by 2 by 256. The channel dimension is wrong here. Okay. So I think we all have understood the shape of the tensor. And what do we do after we have the tensor from the encoder? We pass it through this Q function, which is the quantizer function. And how this quantizer function actually works. Let's actually try to take a look what actually the quantizer function does. So at first, it takes a slice from the tensor. And if you look into the shape of this slice, you will see that it is 1 by 1 by 10. So it's basically a vector, right? So this tensor here is a vector. And if you kind of pass, sorry, give me a minute. Sorry about that. My phone was ringing. Okay. So after we have this vector here, what we do is we perform L2 distance with all the vectors that are present in the codebook. So in the next step, we perform this operation. So z11, z hat 11 is this vector here, and zi is a particular vector from this z codebook. So this is just an element-wise operation. So if you perform this operation, you will see that this vector is the closest to this vector in the codebook because they are the most similar. And after that, we are doing argmin. So we will return the lowest scoring index, right? So we will return 2 here. So this similar operation we will perform for each of these vectors here. So z hat 1 2, z hat 1 3, and z hat 1 4. And after performing the quantizer operation, what we will get is this vector of indexes, right? So this vector of indexes, if you look into the indices, these are all the indices that we have got from this codebook. And if you recall that these indices will actually help us in the later portion of the training, where we will actually train the transformers to generate tokens. So this quantizer actually taken the tensor and actually given us this set of indices. And I also want to clear something out here. Throughout the talk, you will see me. I will call these indices or image tokens or image encoding or anything like that. So don't get confused by that. So because in the literature, you will see that people will call it image tokens, image encoding. So these are all mean the same actually. Okay. So, but the image tokens, if you recall, we are not training the transformers now, right? So we don't actually need these image tokens now. All we are doing is taking an image and we want to reconstruct the image back. So we want to reconstruct the image, and these image tokens, we don't need it now. We actually need a tensor so that we can pass it through our CNN decoder. And the CNN decoder expects a tensor, not this set of not the vector. So how do we get the tensor? Well, it's pretty simple. You just go into your codebook and take each of these vector out. So in the second index, you take the vector. For the 3 index, you take this one, 0 and 50. And then you will get yourself this tensor back, right? Okay, so now that we have a tensor, also something you should notice is these two tensors are not same, right? Because this one is the z-hat tensor, this one we got from the CNN encoder, and this zq vector, zq tensor is the quantized version of this z-hat tensor, because all we are using this tensor is the vectors we have gotten from the codebook. So this is the quantized version of this tensor. So now that we have ourselves a tensor, now we can pass it through the generator or decoder function. And this is just a CNN, which will give ourselves the reconstructed image. And then comes the GAN part. So what the GAN would do is, the GAN, so the discriminator here takes the reconstructed image from the generator, and then it kind of says whether the image is real or fake. So this is basically the workflow. So if our reconstructed image is not very good quality, then the discriminator would say it's fake. Then your loss will be pretty high. So throughout the training, the goal of the generator would be reconstruct very good quality images, so that the discriminator, it can fool the discriminator. And I think now this equation would make much more sense, as you can see this X here representing the image, E is the encoder, and Q is the quantizer. And then we're passing the quantized tensor through the G, which is the decoder, and then we're passing it through the discriminator. So I think now it makes more sense. So we have talked from more of a theoretical point of view, and you will be amazed actually that when you move into the coding part, things actually pretty much look the same. So I just want to give you a brief look into the codes. So this is our model that we have actually trained for the DALL Mini. So here we are initializing the model. You can even try it out. So this is the checkpoint where the model is hosted. So here I'm using an image of 32 by 32 so that I can demonstrate whatever we have seen in the example earlier. So at first, what we do is we call the encode function. So in this encode function, it has two things. So it has the CNN encoder and the quantizer function. So this encode function will return you two things. So it will return you quant states, which is a tensor, and the indices. I think we all know what indices are, right? So the indices is the image tokens that we have gotten from the codebook. So now if you want to reconstruct the image, you call the model.decode function, and in the decode function, you pass the quant states, and then you get yourself the image. You can also actually reconstruct the image using the indices, the vector, because if you pass the indices to the decode function, the decode function actually knows that how it has to build the tensor from the indices, because it has itself access to the code book. So it can actually use the indices to build the tensor, and then it can pass the tensor through the CNN decoder, and you get yourself the image. So if you are wondering what the shape of these quant states and indices are, and if you look at it, it's 2 by 2 by 256. And as you can see, when we did our calculation, it matches with our calculation. Also, the indices here, it's just a 4-dimensional vector. So say the difference between quant states and indices again. Okay, thank you for the question, Ramesh. So the quant states here. Okay, so let me go back to the slide. So this quantizer function, what this function returns actually these indices, right? And how does it get return these indices? Through this operation where we take each of these vectors and calculate L2 distances. So when we calculate L2 distance for all these vectors here, then we get ourselves these indices, right? And now how do we get the tensor? We go to the code book and get each of the vector that are presented here. So in the second index, we take this vector out. For the third index, we take this vector out. 0th index, we take this vector out, and 50th index, we take this vector out, and then we get ourselves this quantized tensor. So this is what we are calling in the coding, in our code, we are calling it the quant states. So this is the tensor we are referring to. Is it clear now? Oh yeah, Thanks for the question. And so actually, ask me if you have any other question. I think we are done with the VQGAN part now. So if you have any more question about the VQGAN, ask me please. How do I update the codebook if it's only used as lookup? So yeah, I'm actually doing a very high level overview. So I'm showing this as just a lookup, but it's not actually lookup. We actually pass the gradient through the codebook as well. So if you look into the loss function, so I'm not actually covering the loss function here. So if you look into the loss function, so in the loss function, we have actually have the perceptual loss and the adversarial loss, where we actually backpropagate through the codebook as well. So in the process, the codebook gets updated as well. Thank you for the question. Okay, so we have actually finished this portion of the training pipeline. So I think now at least some of you understand what's actually happening here. So we are passing our image through the VQ-GAN encoder, and what this VQ-GAN encoder is returning is this image encoding vector. And now I think we all know what this image encoding vector is, right? This is just the indices that we talked about, just the indices from the codebook. Okay, now let's move on to VQ-GAN stage 2. So in the VQ-GAN stage 2, we have ourselves a very good codebook because we have trained it very well, right? So in our codebook, we have very good contextual representation, very good embedding vectors, and now we can actually use the tokens to train a transformer model. And now we will look into the details. How do you do that? So in our DALL Mini, we are actually using a bit different. So we are not using a vanilla transformer. We are using a bit sophisticated transformer model, which is the BART model. And it's a sec-to-sec, which is sequence-to-sequence model. So if you have a sequence and you want to predict or generate another sequence in your output, then this kind of sequence-to-sequence model helps a lot. So now we will look into this portion of the training pipeline. Okay, so let's move on to the sec-to-sec part. So the model we are using is BART. It's from Facebook AI. So the BART actually stands for bidirectional autoregressive transformers. So if you look inside BART, what we will see that it has this encoder and the decoder. And now I think the name meaning also makes sense. The encoder is bidirectional and the decoder is autoregressive. And if you don't know what bidirectional actually means, is if you are using self-attention, then you can look into all portion of your input sequence at a time. So this is what bidirectional term actually represents, that the encoder here is actually using self-attention inside, and the decoder is autoregressive, which means the decoder only uses the past input sequence to predict the future. So this is what autoregressive term represents. So if you are actually familiar with these this kind of models, then you know that these models go through two phases of training. So the first phase is pre-training and the second is fine-tuning. So the way this model was pre-trained, I just want to briefly mention about it. So they have pre-trained the model on an intermediate objective, which is denoising autoencoder. So the way it works is, for example, if we look into the data here, so the way pre-training works is you don't need actually any human annotated labels. So this is why it's very powerful, because the label, we know that labels are pretty expensive. So that's why what you want to do is you want to use the self-supervised objective where you don't need any labels. So you pre-train your model, and then when your model have a very good understanding of something, then you move on to your your actual objective. So the way this model was pre-trained is, at first they have scraped lots of data, text data from internet. So for example, you got this sentence from Wikipedia: Dhaka is a city of Bangladesh. So at first what you do is you hide out certain portion of the sentence randomly. So you take certain words and you kind of add noise to the sentence. And in the literature, we also call it masked input. So this is what it looks like. So Dhaka is a dash. So we have removed this city, and then also we have removed the Bangladesh, and we are using it as input. And in the output, we want our model to actually kind of denoise the input version. So the model has to predict whatever the actual input sentence was. So this is the input and this is the output. So we pass our mask input through the encoder, and the encoder learns a good representation and pass the context through this connection to the decoder. And then what we do is we take our output sequence and we right shift it one bit, and in the first position we add a spatial token, and then we use this sequence as input to the decoder. So if you notice, the decoder is actually having two input. So it has the output of the encoder as input, and also we are giving it an explicit input to the decoder here. And this technique is called teacher forcing. If you are not familiar with that, it's fine. So after that, the decoder kind of predicts what the actual output was, right? So we have given a noisy input, and the decoder has actually predicted or generated the actual input. So this is how basically the BART model was pre-trained. Okay, so this isn't related to our DALL mini, right? Because we in our model we don't want it to generate any text or something like that. So let's move on to our DALL mini stuff. So now we will see how did we actually use the BART model and how we trained it. So in our case, the data actually looks a bit different. So in the this is an example of our training data. So in our training data, we have an input, which is, for example, this text prompt. So it's a painting of Mona Lisa. And in the output, we have a vector. So this vector is our output. So we want our decoder to actually generate this kind of vector, right? So what we do is we pass our text prompt through the encoder, and the encoder is have to learn very good kind of latent representation and kind of pass the whatever context it has learned to the decoder. And then we do is we pass the spatial token at first time step. So then the decoder model predicts what's gonna be in the next. So at every time we're passing one token, and the decoder has to predict what the next token has to be. Okay, so after that we pass the token 2, and the decoder has to predict what the next token has to be, right? And then we pass 43, and the decoder has to predict what the next token is, right? So these are the 4 tokens. So this is the generated tokens from the decoder. And now I have a question for you, which is, so where would we so I think this input here that we are using, I think you know how did we get it. So this input is just the output right shifted. So 243,050, if you right shift it 1 bit, what you get is 243,0, and in the first position we added the spatial token. So this is the input to the decoder, and the decoder has outputted this token. But my question to you, how do we get this vector in our training data in the first place? Where do we actually get this vector before training the BART? Do anyone like to answer? You can write in the chat if you want. So in our training data set, we had this input prompt, which is a text, and also we had an associated vector. Does anyone know where we token from sentences? Actually, it's not token from sentences. Good guess though. Indices of the image, right answer. Is it lookup from the vocab of the words? No, it's not not the words actually. So I think someone has actually answered it. So it's actually the indices of the image. So if you remember from our like, we actually have trained a VQ-GAN already, right? Before training, coming into the BART training BART portion, we actually have a trained VQ-GAN in our hand. So if you recall, in our data set, for every text, we have an associated image, right? So for the text here, a painting of Mona Lisa, we actually have a painting of Mona Lisa image in our training data set. So what we do is we take the Mona Lisa painting image and we pass through our VQ-GAN encoder. And at this point in time, we all know what this VQ-GAN encoder actually does, right? So inside the VQ-GAN encoder, it takes the image and passes through the CNN encoder and the quantizer, and it returns this indices or image tokens, whatever you call it. So this is what we are actually using to train our BART model. So because we know that our VQ-GAN is already trained, so whatever indices we are getting from our VQ-GAN, we want our BART to actually, for the text, a painting of Mona Lisa, to generate these tokens. So the decoder here has predicted 21050, but the actual sequence is 243050. So it means the training is not done yet. We need to do more training. So when we have actually trained the model pretty well, then we will see that when we give the input a painting of Mona Lisa, then we will get pretty close or this kind of sequence as output. So this is pretty much how we train the sec-to-sec model. will the number of tokens of BART be some same number as indices from image? Yep, right. Ramesh have asked a very good question. So this is actually right. So we have to actually make sure, because we don't want the decoder to generate lots and lots of tokens, because we know how many tokens we want. So we actually generate that amount of token from the decoder. So yeah, this is pretty much set beforehand. Okay. So in our actual DALL mini model, I think we are generating 1024 tokens with the BART decoder. Okay. So that's all, I think, for the training pipeline. I think we have looked into the training pipeline pretty well. And at the very last portion, we just saw that how the text goes into the sec-to-sec model. And in the sec-to-sec, we pass the text at first through the BART encoder. And what the BART encoder gives is a vector, right? And then we pass this vector as input to the decoder. And then we give another explicit input to the decoder, which is the VQGAN tokens, right? And we have just seen it here. As you can see in the decoder, we are giving it two inputs. One input comes from the encoder, which is the output of the encoder, and another input comes from this one, which is the VQGAN tokens. So this is the VQGAN token. So this token, we are passing it as input, and with this teacher forcing technique, the decoder has predicted this image encoding. So when you have yourself a prediction, when your model has made a prediction, what do you do? Well, when you got the prediction, you want to use a loss function to check whether the prediction is good or bad, right? So how do we check it? We need a ground truth. So this is our prediction, and we take the ground truth from our VQGAN. So we pass the actual image to the VQGAN, and the VQGAN gives us the actual image tokens. And then we pass two of these distributions through the cross entropy loss, and then we calculate the loss, and then just we backpropagate, and then it's pretty much pretty straightforward. Okay, so yeah, that was the training pipeline. So now let's move on to the inference. So in the inference, you are done with the training, and you probably deployed your model to the server, and your user, or you are interacting with the model as a user, and the scenario gets a bit different from the training phase. So that's why I just wanted to illustrate the inference portion a bit as well. Is that what BART was doing, generating fixed number of tokens so you can use it for pre-training? I'm not sure if I understood the question correctly. Like, okay, I will get back to the question a bit later. Okay. Thank you for the question, though. I will get back to it. Okay. So let's see the inference pipeline first. So in the inference pipeline, so I think we will understand what's going on here, because right now we all know what this BART is doing and how this VQGAN works. So if you look what's happening here, in the inference, we only give a text to the model, right? We don't use any image. So we give this text to the sec-to-sec model, and we know that the sec-to-sec model takes the text and generate an image token. But here we have 3 other tokens. How did we get that? Well, we actually pass the same token through the sec-to-sec model multiple times. And why we're doing it is actually, as you saw in our demo, when you write an image, when you write a text, the model actually gives you multiple results. And this is we are doing because we actually want to show multiple results for the same prompt, so that the user can have a good idea how the generated distribution kind of looks like. So this is just a preference of choice. I mean, you can do that if you want. So we are generating multiple image tokens by the sec-to-sec model. And when we have these image tokens generated, then the recipe is pretty simple, because you want to generate image from these tokens. And how you do that, you use your trained VQ-GAN. So you take your VQ-GAN decoder and you pass these tokens through the VQ-GAN decoder, and the VQ-GAN decoder knows how to actually turn these image tokens into images. So it uses the codebook, remember? So it uses the codebook to turn these tokens into images. So then you have, for these 4 image token for these 4 tokens, you get these 4 images. And after that, we are using another model. And I don't want to go into much detail about this one. It's called CLIP. So basically, I just want to say that we are using it to rank our results. So this CLIP model is very good to rank or sort stuff. So if you give this CLIP model a text prompt, so this one, we pass it through the CLIP model, and also we give the CLIP model all our generated images, then the CLIP model will give us score for each of these images. So this image will probably get 20% score. This one probably get 50%. So all these kind of scores you will get, and then you can actually choose to display the top K images to your user. So here we are actually showing the top 1 results to the user. So this one got the maybe greatest result with the CLIP model. So this is basically the inference pipeline. And now I would like to show you our report. So we have wrote a technical report of the project, and you can actually check it out to learn more about the model, because today's talk was more about how VQ-GAN and BART actually works, not very much about DALL Mini itself. So if you want to learn more about the details of DALL Mini, you can actually check this amazing report. Boris has worked pretty hard on it. So something I would like to show you here is yep, this portion is one of my favorite portion. So here you can see how our DALL Mini was actually evolved during the training. So this is, let me zoom it a bit. So this is after 1 hour of training. This is what the DALL Mini generated for this text prompt: a farmhouse surrounded by beautiful flowers. So it's pretty much garbage, right? So this is the things that it has generated after 1 hour of training. And after 5 hours of training, yeah, it's still not very good, but I think it's kind of learning something. And after 15 hours of training, yep, I think it's getting there. And after 70 hours of training, you can see that it has kind of generated these gardens and these houses and stuff like that. So yeah, this is pretty cool. Yeah, so you can try it out. And also here we have actually kind of compared, give a more quantitative analysis about the OpenAI's DALL and DALL Mini, which you can check out as well. And also some other DALL variants that are out there. And another very important section is this one: limitations and biases. Our model has quite some limitations, actually. For example, if you try our demo, you will see that the model doesn't generate faces of people very well. So these kind of limitations it has. But the good news is we are actually currently working to scale our model and kind of working to reduce some of the limitations and kind of achieve some of the OpenAI level results. So yep, we are working towards scaling the model now. So you can check our report. And I think we have came into the end of the presentation. And I would like to thank everyone from the Delta Analytics team and all of the global teaching fellows. And especially I would like to thank Sarah and Melissa, who have always kind of made sure that we had everything we need, and also gave some great feedbacks in my slides. And lastly, I would like to thank my amazing mentor, Nicole, who has basically actually gave me all the support that I needed to actually make this presentation possible. So yep, now I would like to ask if anyone has any question. I think Ramesh has multiple questions, which I would like to answer now. And also, if I don't get to, you don't get to ask your question here, you can always email me or ping me in Twitter or whatever.
Yeah, we still have some time for questions. So thank you very much, Khalid, for your amazing presentation. And yeah, we already have a lot of questions to answer, but I would like to encourage anyone to write any kind of question you have. So yeah, let's start with questions.
I think I am starting from this one from Ramesh. So how did you guys divide the work? Independently trained or end-to-end trained? Is DALL training both BART and VQ-GAN, or are they frozen? Oh, thank you. This is a great question, Ramesh. So yep, I think if you look into the pipeline, yep. So what we did is actually we trained at first. We trained only this portion of the pipeline. So at first we only trained the VQ-GAN. Okay, so no BART was involved there. We only trained the VQ-GAN because to train VQ-GAN, all you need is image, lots and lots of images. So the objective of the VQ-GAN is to reconstruct images and learn a very good representation in the codebook, right? So we used the VQ-GAN and trained it at first. And when we had this trained VQ-GAN, then we move on to training the sec-to-sec model. And yeah, in the sec-to-sec model, we are using the image tokens that we get from the trained VQ-GAN to train our BART decoder. Because you see, the BART decoder training actually depends on the VQ-GAN tokens. So this portion here, so it actually depends on the VQ-GAN tokens. So so that's why we at first we trained the VQ-GAN and then we move on to the sec-to-sec, and the VQ-GAN wasn't trained later. And yeah, it was frozen, or I wouldn't say frozen. It wasn't actually involved in the whole training of the sec-to-sec. So yeah. And also I should mention it. So if you are curious that how did we actually manage to got this kind of results with only 3 days of training. So if you look closely into the into this figure here, you will see these labels: fine-tuned, random weights, pre-trained. So what this means is we are actually using lots of pre-trained models. So the VQ-GAN that we have trained, it was we actually didn't train it from scratch. We actually took a pre-trained VQ-GAN model, which was pre-trained on ImageNet data, and then we actually took the model and then we fine-tuned it on our own data set. And then we use the fine-tuned version. And in case of BART, we use the BART encoder and it was pre-trained. But the BART decoder, we didn't use any pre-trained decoder because it's pretty straightforward. Because the BART decoder, if it was pre-trained on English language, right? the decoder is pre-trained to generate English language, and in our case, we don't want to use the decoder to generate word tokens. In our case, we are using the decoder for some other stuff. So that's why we are initializing the decoder with random weights and using the encoder with pre-trained weights, because in the encoder we are feeding the text prompt, which is English text prompt. So that's why we could use the pre-trained BART. Yep. I would also like to answer this question. What did you find valuable about your Delta Analytics experience? Yeah, thank you for this question. I think it was a great experience, and I'm kind of sad that it has came to an end. So today is my graduation lecture, but I got to learn a lot actually through the process, and I would say the Khalid from 6 months ago and the Khalid now is pretty different in terms of like presentation skills and teaching skills. And other than that, I have actually learned a lot, like how to build a community, and the support that I have gotten from the whole Delta Analytics team is actually like it's pretty incredible. And yeah, I'm pretty grateful to be a part of it. Thanks. Yeah, thank you, Ramesh. Yep. Did I miss any other questions? Okay, so I think another question was if the quantizer is differentiable. So it's not here. So the idea is pretty not pretty new. I think it was pretty old idea. So I think it was from the VQ-GAN paper. So they use stop gradient to actually make this to flow the gradient through this non-differentiable pipeline. Yep, I would actually recommend to now to go through the VQ-GAN and BART and DALL paper, and I think things would make much more sense. At least I hope after today's presentation. So did I miss any more questions? Thank you, Riddhi.
So if there are other questions that you really want to be answered, maybe write them again. Or yeah, I think we are almost done with time also.
Yeah, and if you cannot ask, and if you have any more question, you can always ping me on Twitter. Or yeah. Thank you, Gaso. Thank you, Reza.
Okay, I think if there are not other questions, we can stop here. So thank you again, Khalid, for your amazing presentation, and thanks everyone for coming today. So as Khalid mentioned, if you have other questions, you can contact him in other ways. And see you at the next graduation lecture then. And thank you again, everybody.
Thank you, everyone.
Bye.